All right, folks, so I'm just going to continue on a bit of the review, a few other topics I wanted to go over in preparation for your exam that we didn't get to finish up in class. So you can feel free to start at this video if you were in class today. So what we left off was getting into the regulation of capillaries. Okay, and just to touch on this a bit here, we spoke about flow to capillaries and how that was regulated by 3 different structures. So we're talking about regulating flow to capillary beds. Okay, and so there were 3 parts or 3 structures that were involved in that regulation. We had the arterioles, we had the precapillary sphincter, and then we had the meta-arteriole. Okay. And now the meta-arteriole, remember, this is the only one that was bypassing or shunting away from the capillary bed. So that's really important to understand how vasoconstriction and vasodilation will affect blood flow to capillaries based upon the action of the meta-arteriole. So the meta-arteriole functions to shunt or bypass blood away from the capillary bed. Toward venules. Okay, so let's look at each of these and how vasoconstriction and vasodilation have different effects on each. Okay, so let's think about vasoconstriction first. So vasoconstriction is going to decrease flow to arterioles, okay? Vasoconstriction is also going to decrease flow to the capillaries as well. So vasoconstriction, let's say that again. Vasoconstriction of the arterioles is going to decrease flow to the capillary bed. Vasoconstriction of the precapillary sphincter is also going to decrease flow to the capillary bed. Remember, these 2 structures are directly flowing to the capillary bed. And so if we vasoconstrict either of these 2 structures, we decrease flow to the capillary bed. The meta-arteriole, on the other hand, is bypassing the capillary bed. And so if I vasoconstrict the meta-arteriole, I'm going to increase how much blood is not going away from the capillary bed, but is going to the capillary bed instead. So vasoconstriction of the meta-arteriole increases flow to the capillary bed. All right, I hope that's clear. Let's look at vasodilation here. So vasodilation, which is opening up that vessel, opening up that structure in case of the sphincters here. If I vasodilate the arteriole, I simply straightforward increase my flow to the capillary bed. If I vasodilate or open up that sphincter, again, I increase my flow to the capillary bed. Meta-arterioles, again, thinking about the function of meta-arterioles, because they're shunting away from the capillary bed and back toward the venule, if I vasodilate that meta-arteriole, if I open up that meta-arteriole, then I am going to decrease how much blood is going to the capillary bed and then increase how much blood is shunting away from the capillary bed going back to the venule. So if I vasodilate my meta-arteriole, I decrease my flow to the capillary bed. Okay, really, really important there. Let's also kind of talk about the factors that influence this regulation. So for arterioles, only for precapillary sphincters and for meta-arterioles, only intrinsic factors regulate this flow. So only regulated by intrinsic or local factors. right? Example, oxygen, right? That's going to be a local factor. CO2, those other metabolites, CO2 and other metabolites. These are the only factors that influence the precapillary sphincter and the meta-arteriole. Arterioles, on the other end, these are regulated by both intrinsic and extrinsic mechanisms. And we talked about those at length during our actual review, but we want to understand here that both intrinsic as well as extrinsic, things like hormones, things like the sympathetic nervous system, things like angiotensin, aldosterone, angiotensin and ADH, or vasopressin, are going to also regulate the state of arterioles and by an extension, the regulation to capillary beds. So both intrinsic and extrinsic regulation. Okay, all right. And then the final thing I wanted to review is actually what we covered in class. So maybe it's a bit better that you kind of step away from this for a minute and then come back to it after you've reviewed what we spoke about in class today. But the final topic is hemostasis, really kind of organizing all that information that we spoke about in terms of hemostasis. Alrighty. And so we spoke about three components to hemostasis. There was vasospasm or vascular spasm. So we had vascular spasm. This was basically the inherent ability of our vessels to constrict after injury. This was also mediated by the sympathetic nervous system. Okay, and so basically under the influence of the sympathetic nervous system, we can vasoconstrict right after an injury. That's going to decrease blood loss. We also spoke about some other factors in terms of beginning to secure that site of injury and create a fibrin clot. So the first part of that was platelet adhesion. All right, let's kind of divide this out here again. So we had platelet adhesion, and then platelet aggregation, and finally our fibrin clot formation. So we have platelet adhesion, and then more mounting of that response, platelet aggregation, and then the fibrin clot formation. Okay, so platelet adhesion basically was von Willebrand factor. So we had von Willebrand factor plus the now exposed subendothelial collagen. So von Willebrand factor binding to the subendothelium or subendothelial collagen, which is now exposed because of that vessel injury. This results in a sticky environment for platelets. Okay, so the initial adhesion of those platelets. We then have platelet aggregation. So how we start to, via positive feedback, aggregate more of those platelets via some of the substances that those platelets secrete. So platelets that begin to aggregate here initially will then secrete a couple of substances. So platelets will secrete ADP, let's say one, ADP or adenosine diphosphate. It also secretes serotonin, epinephrine, right? ADP specifically is going to aggregate more platelets, right? So aggregate more platelets, okay? And this is going to be positive feedback. The other important thing that they secrete is thromboxane A2. Okay, that is going to secrete more ADP, right? Again, more positive feedback. It's also going to increase platelet aggregation, so more platelets coming to the site. As well as cause some further vasoconstriction. Okay. Let's look at the third part of this, that fibrin clot formation. So essentially we had two major pathways to our clotting cascade. And the first thing we want to identify is that clotting factors are always circulating in the blood inactivated. All right, so in its inactivated form, it's just a Roman numeral, or just that number of that factor, but then when it's activated, it's gonna have that A next to it, right? So the activated form has that A, right? And these are made by the liver. Second thing we wanna understand is that these are made by the liver. Okay, so let's look at the extrinsic pathway, which is then converged with the intrinsic pathway. And again, don't be too worried about the details of what's happening upstream here and upstream here, but really where they converge. So they converge via the conversion of factor 10 in the inactivated form to factor 10A. Okay, and remember, this is going to require, factor 10A is going to further convert prothrombin to thrombin, and together with the help of some cofactors here, so tissue, so protein factor 3, along with calcium, along with factor 5, all three of these are going to work together to then convert prothrombin to thrombin. All right, so we've got prothrombin, also called factor 2, by the way, is now being converted to thrombin. Okay, thrombin, we said, has 3 roles, right? Let's put those in another color here. So thrombin has a positive feedback to the proximal parts of this cycle, or this cascade here. In other words, thrombin is saying, send more clotting factors, activate more clotting factors upstream, and send them down to make more thrombin, essentially, to positive feedback onto itself. The second job, so this is the first job of thrombin. The second job of thrombin is to activate fibrinogen, the inactivated form. So fibrinogen in its inactivated form can now be converted to fibrin. But this is the loose meshwork, right? This is not stable, loose or unstable meshwork or mesh, okay? And then the third job of thrombin is to activate factor 13. So the third role of thrombin here is activation of factor 13. To 13A, so a small arrow here to factor 13A, and then factor 13A will then convert fibrin into the more stable fibrin clot. So let's draw that in a different color. That's kind of the culmination of this entire cascade. So now we can convert that loose unstable fibrin mesh to a fibrin clot, which is stable, okay? And that is done with the help of factor 13A, which is converted to its active form via thrombin as well, okay? And so this fibrin clot is going to be the more stabilized, secure fibrin clot that kind of seals up that injury. All right. Last thing I'll go over here is kind of how we regulate clotting, right? We spoke about the fact that clotting should not be happening indefinitely. It definitely needs to be regulated. And so we'll go over how we regulate that clotting, as well as how we can dissolve existing clots. So in healthy endothelial cells, we have a couple of things that prevent platelet aggregation. So that's one way that we can inhibit clot formation, is by preventing that initial platelet aggregation. So we can secrete prostacyclin, also called prostaglandin inhibitor, right, as another name, as well as nitric oxide. And these two things will inhibit that initial platelet aggregation. Okay, that's kind of the first way that we can keep healthy endothelial cells and prevent clotting. The second thing that we can do was that tissue factor pathway inhibitor, TFPI. And tissue factor pathway inhibitor specifically blocks the extrinsic pathway, right? So this blocks what we just drew out, but specifically the extrinsic part of that. Okay. And then the third way was thrombomodulin. And thrombomodulin is going to block both pathways. This can be, again, converted into protein C, and that has an anticoagulatory effect, but it blocks both of these pathways. Okay, so thrombomodulin blocks both intrinsic and extrinsic pathways. Oops. So blocks both intrinsic and extrinsic pathways. And this is really done by the conversion, the production of protein C. And protein C is an anticoagulant. In other words, it wants to prevent coagulation or prevent blood clotting. All right, so this is really preventing blood clotting. Let's look here lastly at how we dissolve existing clots. Right, so this we think about as prevention. And then on the other side, we can think about dissolving those clots, which is kind of like the cure, right? Prevention versus cure. So we've got the dissolving of clots. And this is mainly done by plasmin. Okay, plasmin can enzymatically dissolve fibrin clots. Okay, but plasmin needs to be activated. And so we can activate plasmin. So a couple of layers here. This is kind of complex, so make sure you're following here. Plasmin can directly dissolve the fibrin clot, but plasmin needs to be activated from the inactive form, which is plasminogen. So TPA, or tissue factor, right, so TPA, or tissue plasminogen activator, is what is needed to activate plasminogen to plasmin. Okay, and then the third kind of layer here, which really adds some complexity, is that fibrin, the fibrin clot that is trying to be dissolved, the fibrin clot itself, so fibrin secretes that TPA, right? All right, so just to kind of clarify here, the clot itself, fibrin, will secrete TPA. TPA will convert plasminogen to plasmin, and then plasmin will degrade that fibrin clot. All righty. Okay, so that's all I have in terms of additional topics to review. If you've got questions between now and the exam, please feel free to reach out by email, and good luck again on your exam.